In this video, I want to talk about the future evolution of stars like our sun, how a star like our sun changes over the course of its life. We looked at the Hertzsprung-Russell diagram. It's really just a classification scheme for different types of stars. There are main sequence stars that range from hot, bright, O type stars, O, B, A, F, G. The sun is right about here, and then dim, cool, red, K and M stars at the other end of the HR diagram. There are also stars that are much bigger than main sequence stars and much brighter. Those are your giants and supergiants, and there are also stars that are much dimmer than main sequence stars for their temperature, which leads us to conclude that they are smaller. So down here you have your white dwarfs. That doesn't tell us anything about these stars and why they are different from one another. It doesn't tell us anything about the star's history. They could just be different stars. There could be some little tiny stars and some great big giant stars, and they're just different. Or these different types of stars on the HR diagram could represent different stages in the life cycle of a star as it changes over time. The way if you took a big picture of a crowd and you saw some infants and toddlers in the crowd and some full-grown adult humans in the crowd, you might conclude that there were just different kinds of animal if you were an alien from another planet, right? There are little tiny humans, there are 5 foot, 6 foot humans. But if you watched humans for a long time, you could see that the little tiny ones turn into big humans. We can't do that with stars because stars take billions of years to live their lives. So we can't watch a star and see if it changes from one kind to the other. That would be a very slow and possibly incredibly rare process. What we have to do instead is construct a model for how we expect stars to change over the course of their life that explains the stars that we see in the sky, and that is what we do. To start, let's review the process that powers stars. The process that powers stars is nuclear fusion of hydrogen, which typically in an atom consists of 1 proton and 1 electron. In a star where it's very hot, this hydrogen usually exists as a plasma. In other words, the electrons and protons aren't paired together, they're just zipping around willy-nilly. Hydrogen has 1 proton, 1 electron, and you can fuse 4 hydrogen atoms into 1 helium. In this process, you can think of a proton and an electron as turning it into a neutron. That's not exactly what happens. We may talk about the nitty-gritty details of that process in a separate video. But in the process of fusing a hydrogen into a helium, this is a helium-4 nucleus, 2 protons, 2 neutrons, that process involves fusing these particles together in a bound nuclear system. If you look up the mass of 1 hydrogen atom and multiply that by 4, you get 4.03 atomic mass units. If you look at the mass of 1 helium atom, that is 4.0026 atomic mass units, which means the mass of 4 hydrogens is just a little bit more than the mass of 1 helium. That mass, that loss of mass, is where the energy of a star comes from via Albert Einstein's E equals mc squared. Energy can be created by the conversion of mass into light, kinetic energy, all sorts of energy. And the c is the speed of light, which is a very big number. So c squared is a very, very big number. And the amount of energy you get for losing just a tiny, tiny bit of mass is huge. That is enough energy to power a star for billions of years, converting some hydrogen into helium every second. In our sun, this process only happens in the core. In fact, in all stars, this process only happens in the core. The part of the sun we see is not hot enough for there to be nuclear fusion. The temperature is only thousands of degrees. The pressure is only hundreds of atmospheres. But in the core of the sun, the temperature is millions of degrees Kelvin or Celsius. And the pressure is trillions of times the atmospheric pressure here on Earth. The atoms are moving fast, or the hydrogen nuclei, the protons, are moving around fast, and they're also being pushed very, very close together by the force of all of the mass of the sun's gravity being pulled into the center. That high temperature and high pressure is what you need in order to fuse two protons together. Two protons don't really want to be fused together when they're far apart. A proton has a positive charge and the other proton has a positive charge. Electrically, they want to repel one another, but if you bang them together hard enough, the nuclear force overpowers that repulsion and sticks them together. So fusion only happens in the core of the sun, and convection and radiation carry that heat from the core to the surface. There's no fusion happening on the part of the sun we see. Only the middle, say 20-25% of the volume of the sun has got nuclear fusion happening in it. That fusion has been happening for about 5 billion years. The sun's about 5 billion years into its life and has continued at roughly the same rate. The sun actually started a little dimmer and has gotten a little bit brighter since it first formed. But for the most part, when a star is a main sequence star, it fuses hydrogen and helium at a pretty constant rate and gives off energy at a pretty constant rate. This current state of the sun is one of balance between two opposing forces. Gravity wants to squish the sun smaller and smaller and smaller. All of the sun's mass is pulling on all the other sun's mass, and that wants to make the sun pull in. The heat from the nuclear fusion wants to blow the sun up. It wants to make the sun bigger and bigger and bigger and bigger. When you heat up a gas, it expands. When you set up a nuclear bomb, it explodes. So these two opposing forces, gravity pulling in and thermal expansion pushing out, are, in the case of our sun, exactly balanced between one another. We call that state of balance hydrostatic equilibrium. It's a lot of words to just say the inward force of gravity and the outward force of the explosive thermal expansion of all this nuclear fusion are balanced against one another. And when a star is stable, that balance can hold for billions of years. It's worth noting that this balance is, this equilibrium is stable. In other words, if it starts to go off in one direction or another, it will restore itself. Let me give you an example. Imagine, for some reason, that the fusion in the core of the sun started to slow down. What would happen? Well, it would give off less heat. If it gives off less heat, then there's less force of thermal expansion. That will cause gravity to start to win this fight between these two forces. Well, if gravity starts to win, it squeezes the hydrogen in the core together with a greater and greater pressure. That will bang the hydrogens together with more force. It will cause the rate of nuclear fusion to increase. That will cause more heat, and that will cause the star to expand again. So the trade-off between these two forces is it's what's called a stable equilibrium. If it starts to drift off, it will be pushed back to the center, which is fortunate for us. It keeps the sun stable for billions of years. It's worth noting that the more mass a star has, the greater the rate of nuclear fusion. A star that's more massive than our sun will squeeze the hydrogen in its core harder. And because it squeezes the core harder, it bangs those hydrogens together faster, harder, and more often, and the rate of fusion is faster. You might think that a bigger star with more hydrogen would live longer. That's not true. A bigger star with more hydrogen burns faster and actually burns itself out faster than a low mass star. So the general rule for main sequence stars is stars the age of the sun live for about 10 billion years or so. Stars with less hydrogen, less mass, last for longer. Stars with more hydrogen, more mass, last for more time. So the more massive a star is, and I have to be careful not to say bigger, because stars, we'll see in a minute, change their size over the course of their life, but they don't change their mass. Stars with more mass live for a shorter amount of time because they burn their hydrogen faster. If we look at the HR diagram, we're a G-type star. There are stars with hundreds of times more mass than the sun, and there are stars with 1/100th as much mass as the sun. Stars live on this main sequence for a finite amount of time. And what we'll see is our theories of stellar evolution predict what happens to stars after they run out of hydrogen for the process of nuclear fusion. And that's what we want to talk about next. So what happens? We take a look at the core of our sun. It is fusing hydrogen into helium. That means that over the past 5 billion years, the sun has cooked up a bunch of helium in the core. That helium doesn't do anything but just sort of sit there and get in the way. So the core of the sun is accumulating helium nuclei. Those helium nuclei, by the way, can't fuse with each other in our sun because 2 helium nuclei have 2 protons. 2 protons, 2 protons. The force of repulsion between 2 helium nuclei is 4 times as great as the force of repulsion between 4 hydrogens. So in order to fuse 2 heliums together and make them stick, you would have to push them 4 times as hard as you have to push 4 hydrogens. So the helium just kind of sits there and gets in the way. For most of the life of the sun, that's not a problem. There's plenty of hydrogen to fuse into helium. This helium waste is just atomic nuclei banging around in the nucleus, banging off the hydrogens, not really causing much of a problem. But eventually, there will be so many helium nuclei in the core of the sun that they sort of get in the way of the hydrogens and keep them from banging into each other. When that happens, the rate of fusion in the core will start to decrease. This will be noticeable from the outside eventually because it will change the amount of energy that the core of the sun is producing. So when the amount of helium begins to outweigh the amount of hydrogen in the core, this will slow down the rate of nuclear fusion. This will cause the core to cool down. What effect will that have? Well, remember, the current structure of the sun depends on this equilibrium between these 2 opposing forces. If you shift one of them, the other one has to shift to compensate. So if the temperature of the core starts to drop because the rate of fusion is decreasing, that means that gravity will start to win this tug of war between these 2 opposing forces. So the gravity pulling all of this material in will start to overpower this outward force of thermal expansion, or this outward tendency of the sun to expand because of the heat that is generated in the core. This will compress the core and squeeze it. When you compress a gas, it heats up. So this compression of the helium-rich core will now cause an increase in temperature. And that increase in temperature will happen in the region around the core, causing it to heat up. So you see that this balance starts to shift to a new normal. That new normal will heat up parts of the sun that didn't used to be hot enough for nuclear fusion to happen. In other words, the collapse of the inner core will heat up this shell around the core where it wasn't hot enough for fusion to happen before, and now make it hot enough for fusion to happen there. This is called the shell burning phase that the sun will reach in about 5 billion years from now. So the sun's about 5 billion years old. We've had a good 5 billion year run up until now. There's another 5 billion years before anything weird starts to happen in the core of the sun. So the compression of the helium core jump-starts a shell of fusion around the core, and that actually increases the temperature again so much that it causes the sun to expand and resets this equilibrium between gravity and thermal expansion to a new set point, a new equilibrium point. When this starts to happen, this isn't particularly good news for anything left living on the Earth, if anything's left living on the Earth in 5 billion years, because the sun will get much brighter. It will, even though it's cooler on the surface, because you've taken that heat and you've spread it out over a bigger volume, the sun will get cooler and redder on the surface, but it will also get brighter in the sky and give off more radiation to the Earth. So in this process, the core heats up. That expands the star, but the surface of the star cools and gets redder. At this point, the sun won't be a main sequence star anymore. It will move off the main sequence part of the diagram and become what's called a subgiant. If we look at the HR diagram, the sun's about here. Actually, the sun's more like there, but it's sort of in the middle of the HR diagram. After this shell burning phase happens, the sun will get cooler and brighter, which takes it from here to here on the HR diagram. It's called a red subgiant. And during this process, which will last millions of years, the core will continue to contract as fusion is blocked in the core by the helium, and gravity wins that fight in the core, but that generates heat that heats up the shell around the core. It's actually a super complicated and interesting process. As this happens, the core of the sun will, or the shell around the core of the sun will get hotter and hotter and hotter. The sun will expand more and more and more, and the surface will get bigger and bigger, but cooler and cooler. So the sun expands and cools as its core has found this new source of heat energy. This phase of the star's life is very short. It might last for only 100 million years. Now, 100 million years seems like a long time to you and I, and it is a long time. But to a star that has now lived for 10 billion years, this is only 1/100th of its lifetime, right? The sun's 5 billion years old now. In another 5 billion years, this will happen. That's 10 billion years before the sun starts to enter its old age, which is sort of what we're talking about here. Well, 10 billion years compared to 100 million, it's like 1 year compared to 100 years, right? This is a very short process in the grand scope of the life of a star. What happens next? So the sun's a subgiant now. What do we mean by giant? How big will the sun get? Well, if we take the radius of the sun now as r, when it starts the subgiant phase, it'll get about 3 times bigger. When it ends the subgiant phase, it might be as big as 100 times larger. Okay? Imagine the sun in the sky 100 times larger. How big is the sun in the sky? The sun's about the size of your pinky held at arm's length, or about the size of an Advil. If you hold an Advil up to the sky, that's about how big the sun is. You might think, that doesn't seem right. It seems like the sun's bigger than an Advil. Well, it's because of the light of the sun. If you actually see the sun at sunset, it's really, really tiny. Imagine that being 3 times bigger, about the size of, say, a quarter in the sky. Now imagine that being 100 times bigger, about the size of a beach ball held up at arm's length. The sun will get very big, very bright, give off more. Its surface is cooler, but it will be giving off more heat and light. The temperature of the Earth will start to increase. The oceans will all evaporate. Not boil, but the oceans will all evaporate. And the Earth will probably become uninhabitable, at least in the way that it is habitable now, by plants and animals that need water to survive. If the Earth is still habitable by the end of this subgiant phase, it will probably be mostly bacteria and things that have figured out how to live in very unforgiving environments. The next thing that happens to the sun will be dramatic, which is this process continues. Fusion keeps on making helium. That helium isn't doing anything much but getting in the way until the rate of fusion in the core starts to drop so much that gravity really takes over. And gravity's like, all right, the core is cool now. I can really squeeze this matter together. Gravity pulls everything together. And now, that pressure in the core of the sun will get high enough that these heliums, with 2 protons each, are squished together hard enough that they can start to fuse together. This event that will happen in about 5 billion years is called the helium flash. Now, all of a sudden, instead of just fusing hydrogens into helium in the core of the sun, all of this helium that's just been hanging around getting in the way for 10 billion years will start to fuse into heavier elements. 2 heliums can make a beryllium, 3 heliums can make a carbon. Both those processes give off energy. So now it's like the sun suddenly has a new source of fuel. The core is being squeezed hard enough to fuse helium into heavier elements, and that process gives off heat. And that heat will heat up the core, it will heat up the sun, and it will cause the sun to expand even more. So after the helium flash, the sun starts to get hotter and hotter, moving this way on the HR diagram, right, to the hot end of the axis, and bigger, turning it into an honest-to-goodness red giant. So a red giant is a main sequence star that has run out of hydrogen fuel but is now burning helium as an energy source. This stage of the sun's life is, again, very short. It might only last for 50 million years or so. The sun is on life support at this point. It doesn't have much time left. It's going to fuse this helium fast because that pressure in the core is squeezing it really, really hard. And this process might only last for 50 million years. So the sun will spend 50 million years or so as a red giant fusing helium into beryllium, carbon, maybe a few slightly heavier elements than that. How big are we talking about when we say a giant? Well, the sun right now, if this was to scale, the sun would be just a tiny, tiny dot. So here's the orbits of Mercury, Venus, Earth, Mars, and Jupiter relative to the sun. When the sun becomes a subgiant, it might get as big as the orbit of Mercury or Venus. By the end of its giant phase, it might be as big as the orbit of Venus. When the Earth, that's about half the size of Earth's orbit, if it's a little less than the orbit of Venus. We can't predict exactly what these numbers are, but we can make guesses from looking at other giant stars, right? When the sun becomes an honest-to-goodness red giant, it will expand to probably larger than the size of the Earth's orbit. So when the sun is a subgiant, the Earth's going to get cooked by the heat of the sun. When the sun is an actual honest-to-goodness giant, the Earth is probably going to be engulfed by the sun and just evaporated by being essentially part of the sun now. It might even get almost as big as the orbit of Mars. Again, these aren't exact predictions, but they're based on I have no idea what happened here with my spelling. They're based on models of how much mass there is in the sun, how fast this rate of fusion will happen, how much heat that will generate, and then how much expansion that will generate. So the Earth is a goner by the end of the subgiant phase and evaporated essentially during the red giant phase of the sun. That's not something to concern yourself with. It's 5 billion years in the future. If anything resembling humanity is around in 5 billion years, presumably we will have figured out some way to move to one of the moons of Saturn, or maybe out of our solar system entirely. Or humans will be extinct for some other completely different mundane reason well before 5 billion years from now. Keep in mind that is longer than the current amount of time life has existed on the Earth. So speculating about what might happen to humanity after billions of years is silly. What happens next? What happens to a star after it's a red giant? Well, one thing to realize is that when a star is a red giant, some of its mass is now very, very far away from the rest of its mass. And essentially what happens is that those outer layers just kind of leak out into space. The solar wind pushes them out into space, and the sun winds up as this diffuse, expanding envelope of hydrogen that you can't really call a star anymore, except for the core, which is left behind in the center. We see examples of this when we look out into space and look at things called planetary nebula. I think I said in another video, nebula is a very general purpose and almost meaningless word in astronomy. All it means is cloud. Some clouds are places where stars are being created. Some clouds are places where stars blew up. Some clouds are actually not clouds at all. They're galaxies. We just didn't know they were galaxies when our telescopes were worse in the 1800s. Some nebula are little perfectly round circles, like a little soap bubble. And these were called, when they were first discovered, in the 1800s with eyeballs looking through telescope, planetary nebulas, because they kind of look like Jupiter. They were a little round circle. They have nothing to do with planets. They are not in our solar system. They're not places where planets are being formed. The word planetary nebula just means little round cloud. What are they, though? What are they? Are these expanding bubbles of gas that had been a red giant. And what you see in the center of every planetary nebula is a little tiny, very hot white star, a white dwarf. So we see these all over the place. They're really pretty. I'm trying to get to the next one here. Okay, there's another one. That's the Ring Nebula in Lyra. This is one that almost looks like a whirlpool, the way it's swirling. But in the center of every one, white dwarf, you see this tiny, tiny, small, hot, bright. Well, for its size, bright for its size, right? Because it's super, super hot. Star. What is that white dwarf star? That white dwarf star is the exposed core of what had been the red giant. This expanding bubble of gas is the outer layers of that red giant escaping into space. So a planetary nebula is the expanding outer layers of a star that has gone through old age, passed through its helium flash, and is now just a hot core of helium and hydrogen. And beryllium and carbon, right? Because the helium's been fusing into carbon now for a few 100 million years. That's what a white dwarf is. So once fusion ends and the outer layers evaporate, the exposed core of that star is a white dwarf. In a white dwarf, there really isn't any nuclear fusion happening anymore. A white dwarf is like an ember left in a fireplace. It's not on fire. Right? It's just still hot because it had been on fire for a really, really long time. It's like a burned out coal in a fireplace. So there's no fusion happening in a white dwarf, but it's still hot from being a star for a billion years. They're mostly made of carbon. At least our sun's white dwarf will be mostly made of carbon from the fusion of helium into beryllium and carbon. And it could stay that way, just giving off light because it's still hot, for tens of billions, maybe even hundreds of billions, maybe even a trillion years before it cools off all the way. Our universe isn't even a trillion years old. We would expect over time to see these white dwarfs cool off and get yellow and then orange and then red, but the universe isn't old enough for that to have happened yet. Any white dwarfs that were created in the universe are still white hot from having been the cores of stars for billions of years. But that's all a white dwarf is, at least in this model of stellar evolution. It is the leftover, burned out, still hot core of a main sequence star that had its helium flash, turned into a red giant, and when fusion ran out, those outer layers evaporated, leaving behind the white dwarf. So that is the life cycle of our sun. Our sun started as a main sequence star, started a little bit dimmer than it is today, got a little bit brighter over time, but mostly stayed stable with the same temperature and the same brightness for 5 billion years so far. Another 5 billion years. The balance between its gravitational pull in and its thermal expansion outward will shift. It will become a subgiant until that point where it reaches its helium flash, when it will become an actual honest-to-goodness red giant. After that, 50 million years or so long process of fusing helium into carbon, it will run out of options, essentially, and the fusion will stop, the outer layers will leak away, leaving behind a white dwarf that will, over the next hundreds of billions of years, gradually get cooler and cooler and cooler and dimmer and redder and redder. That is what the future of the sun looks like. It's worth thinking about, what about stars that are not like the sun? The sun's got enough hydrogen to remain a main sequence star for 10 billion years. I already said that more massive stars will burn out faster. Type O, B, A stars might only live for 1 million years, 2 million years, 5 million years before burning themselves out very, very fast. Whereas very dim, cool K and M stars have much less mass, so they're squeezing their hydrogen more slowly, so they're burning it at a slower rate. So even though they have maybe a tenth as much mass as the sun, they will live for 10 times longer. In fact, stars down here at this end of the HR diagram will never ever even have their helium flash. There's not enough mass to squeeze that helium together to make it fuse into beryllium and carbon. So they'll just kind of die off down here at the bottom of the HR diagram. But what about stars that are more massive than the sun? How are they going to wind up in their old age, in the last stages of their life? Will they go through the same phase of subgiant, giant, white dwarf, or will they do something different? That is a very interesting question that we will talk about in another video.